The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Problem 17 tells us that two traveling waves, and they gave us the equations, which I'll write on the board in a second, are superposed on the same string. The distance between the adjacent nodes of the resulting standing wave is blank. So, they gave us two equations. Y1 is equal to A sine of K x minus bt, and y2 will be equal to A sine of k times x plus bt. Now, right off the bat, you guys hopefully should notice that these are not the standard way of presenting the wave equations in the book, but they're perfectly acceptable ways, and if that happens, just kind of chug along with what you know and should work out for you. Don't be too intimidated. The formula is slightly different. Now, they're asking us to basically analyze the resulting standing wave. We have to figure out where the nodes are going to be on that. So we need to get the equation of the resulting standing wave. And this is going to be the tricky part because this is where some trig properties come in. So in your book, I believe it's equation, what is that, 1650, or it's in your Waves 1 chapter. There's an equation that tells you how to add two sine functions together. So we can say that if we have sine of alpha plus sine of beta, where alpha and beta are going to be your terms, k times x minus vt and k times x plus vt all, those two add together as 2 sine of 1/2 alpha plus beta times cosine of 1/2 alpha minus beta. Okay? So it looks a little messy, and it'll take a second to do the algebra, but it's doable. So this is going to be our alpha, and this term is going to be our beta. And we can't forget about our amplitude, so we're writing the equation that's going to plot in the front. It's just a coefficient, so it doesn't matter, and they're the same coefficient, so we can actually just factor it out. If they're not the same amplitude, then you really can't add these waves together. So plugging all this in, we're going to end up with y prime, which is going to represent the formula for our standing wave, is going to be equal to 2a sine of 1/2 k times x minus dt plus k times x plus dt times cosine 1/2 k times x minus dt minus k times x plus dt. So all I'm doing in there is just for alpha plus beta, I'm plugging in this plus this, and for alpha minus beta, this minus this, okay? And like I said, we can't forget our amplitude coefficient out front. So I highly recommend that you go through and kind of reduce everything. I'm just going to go ahead and write out what the final equation is going to look like. When I did it, I just kind of distributed all the individual terms, and a lot of stuff canceled out if you can't tell by looking at it. So we end up with sine of kx cosine of negative kVt times our 2a, of course. So this is going to be the formula for our standing wave. All right? Which is going to be the combination of the two waves that they gave us on the same string. Now, we're looking for locations along the wave. We're not looking for times at which the wave is going to be there. So what we're going to be concerned about is this sine function right here, because this sine function holds that variable x. Now, concerned about, because like I said, we're concerned about our location, so we're not even going to care about the cosine term. Now, if we're looking for a node, basically, if you have a standing wave, it's just going to look something like that. And this is just going to flip back and forth, this is going to flip back and forth, so on and so forth. And these are our nodes, where the actual wave itself, the vertical displacement, is going to be equal to 0. So what we're looking for is when this sine term is going to be equal to 0. If this is equal to 0, everything multiplied by it turns out to be 0, and the y prime value actually ends up being 0. So what we want to know is, when does sine of kx equal 0? Now, we know sine is equal to 0 basically at 0, pi, 2 pi, 3 pi, 4 pi. So what we're looking for is kx needs to be equal to some multiple of pi. Alright? 1, 2, 3, 0, like I said. N is going to be equal to 0, 1, 2, 3, etc., depending on how long the wave's actually going to be. So once you get to this point, you're almost done, because now we can look and say, well, x is going to be equal to n pi over k. Alright? That's our formula, where n still is 0, 1, 2, 3, or whatever. And that'll give us our location. Now, they don't actually want locations of the nodes. They want to know the distance between each and every one of those nodes. Okay, so if we figure out 2 or 3 of them, we can start to see a pattern. So the first one's going to occur when n is equal to 0. So the first node, of course, occurs right where the wave starts, wherever that boundary is going to be. Now, the second one is going to occur when n is equal to 1. So that's going to occur at pi over k. Okay? Now k is still a variable, but everything they gave us is variables, so that's fine. They didn't give us any numbers or anything. Next one occurs at 2 pi over k, and with those 3 we can definitely start to see a pattern. Next one's going to be 3 pi over k, 4 pi over k, etc., etc. Now, that gives us our answer, because we're just looking for the distance between the adjacent nodes. So the distance from x1 to x2 is going to be pi over k. x2 to x3, pi over k. To go from pi over k to 2 pi over k, that's just 1 pi over k. So, assuming the pattern continues, which it does, our final answer is just going to be the distance is pi over k. That is going to be the distance between the nodes. Whatever our k value is, just divide it into pi, and that's how long the horizontal displacement is between each node on this standing wave.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.